Here's our next video for section 2.2. I want to talk about a concept of how many solutions a system has, but first just a quick review of the vocabulary to make sure it's clear. First of all, what is a linear system of equations? We had an example of it last time, but it's a system of more than one equation. It's just a collection of equations, and it's a linear system if the two equations are linear equations. And these two equations both happen to be linear. Now, a solution of an equation in general is values of the variables that make it true. In this case, a solution of a system has to make both of the equations true. So the point 2, 1 is a solution of this system, because if you plug in x equals 2 and y equals 1, you'll get 2 plus 1 is 3, and 2 minus 1 is equal to 1. So and you can actually, if you want to find that solution, you could graph it like so, and you would get the point 2, 1. Now, let's look at some other things that can happen. What if the points don't, or what if the two lines don't intersect at a nice single point like that? Let's think about what can happen. So here's an example. We want to solve each system. In order to do that, I want to graph each of them, if we're doing it the same way. And in order to graph it, we need to solve for y in terms of x first. Here, I labeled them as equation number 1 and equation number 2 for part A. Equation A is already written for y in terms of x, but we still need to work with equation number 2 here. So I'm going to subtract the 2x from both sides, like so. Now to get the y by itself, we need to divide both sides by 2. Remember, if you're dividing the entire right side by 2, you're going to need to essentially distribute it into the two terms, and that will come out as we'll see. And so this is the same as equation number 2 that we have here. Now that equation is equivalent to this one that we have. Let's think about what this will look like if we graph it. Let's consider what the the y-intercept of this one is, and what is the slope, and what is the y-intercept and slope of this. Well, equation number 1 has slope -1 because of the negative right here. It's -1 times x. And the y-intercept is the number 5. And equation number 2 also has slope -1 because that's like a -1 times x right there. You could just think of it as -1x if you want. And the y-intercept is 3/2, also known as 1.5. So if you graph these, here's what it will look like. So you end up with these parallel lines here. They have the same slope, so that means they're going to go in the same direction at the forever, kind of like railroad tracks do, except these are going to go even longer than railroad tracks, because railroad tracks are all of finite length and the Cartesian plane is infinitely wide. So and also railroad tracks cross each other sometimes when you have like a junction and one kind of turns into the other one. So these definitely never intersect, and that's always going to happen whenever they have different y-intercepts here. That one's right here, this one's right here, but they have the same slope. So you're going to have no solution for this. There's no point that is on both of the lines. So let's try the same thing with B. I'm going to solve both of these for y in terms of x. You can try it yourself first to get some extra practice, and we'll see what happens. I'll call this one equation 1. This one is going to be equation 2. And I want to point out a trick here at this stage while you were solving this equation for y in terms of x. The trick is that if you have a fraction times y and you want to get y by itself, like we have here, a thing you can do is just multiply both sides by the reciprocal of that fraction. So if I just multiplied it by 3, that would cancel out with the denominator. But then if you also divide it by 2 at the same time, in other words, just multiplying by 3 over 2, that will, both the top and the bottom will cancel out, and you'll just get y. But of course you have to do the same thing on both sides. On the right side you have to distribute it, so we'll get 3 over 2x. 3 times negative 3 is going to be 9 over 2. So there is that. That's equation 1. Let's try equation 2 now. I'll pause it to skip ahead so you don't have to sit through it. You'll get something like this. And what you notice here is that these two equations are saying exactly the same thing. They are, in fact, equivalent to one another. So if you're going to graph it to find what points they'll have in common, they're going to have all the points in common. This is what it will look like. Now, when you graph them, they're the same equation. So here are all of the solutions of one equation that you can see. Maybe you can sort of tell it's green. And then here are also the solutions of equation number 2 that you can see are purple. So if you want to find solutions, you could say, here's a solution. X equals 3, y equals 0 should make both of these equations true. Here's another one, 1, negative 3. There's another one over here, 0, negative 4.5. And you get the idea. There's an infinite number of solutions because there's an infinite number of points on this line. So that's the moral of what I wanted to talk about right here, is that there's 3 possibilities. There's always going to be 3 possibilities. You have an infinite number of solutions like this. If the equations are really the same equation, you're going to have no solutions, which will happen here if they have different y-intercepts but the same slope, which will make them parallel and never intersect. Or you're going to have one solution, like this case. So I just wrote this out to summarize that. And I also wanted to point out that there is some vocabulary in the book that you do not need to know for my class. It's not going to come up again. You might see it in the textbook here and there, but don't worry about it. These are just special words to describe these different types of systems. There's consistent and independent systems, inconsistent systems, and dependent systems, which just describe these 3 situations I'm talking about. But you don't need to know that, so just letting you know.